Welcome to the BIRCH Methods Core workshop. I'm Gary Chen, a faculty investigator at the Center and professor of Biostatistics. Today, we are delighted to invite Professor Jim Hughes of Biostatistics, a colleague of mine who is a well-renowned expert in stat wedge and related designs, to introduce and discuss those designs with the audience. Jim has extensive experience in statistical methodology research motivated by problems in HIV/AIDS and other sexually transmitted diseases, and his seminal paper on stat wedge design is widely cited and applied in mental health, HIV, and implementation science research broadly. Without further ado, let's welcome Jim and get started.
All right, thanks very much, Gary. So I will share my screen here. And all right. Well, thanks everybody. Thanks for coming. And what I just want to mention or reiterate that please feel free to interrupt me at any time. This teaching on Zoom is always a little clumsy in that respect because I can't really see you as I'm just looking at my screen here, but just feel free to interrupt or put something in the chat and then the host will interrupt me. So so what I'm going to talk about today is a little introduction to cluster randomized trials and then perhaps a little more depth on the stepped wedge design. And so let's just start with sort of the basics is what is a cluster randomized trial? And the idea of cluster randomized trials is when you randomize not individuals as in your classic clinical trial like the vaccine trials that we saw for coronavirus and so forth, but rather we randomize groups of individuals, such as entire towns or cities or families, health clinics, something like this. But you do measure the outcome on individuals within the group, and in such a trial, the key thing to remember is that the unit of analysis then becomes the group. So you have to have replications at the group level. So a common error that people make is they have, say, 2 villages or something, 1,000 people in each village, and they flip a coin and one village gets the intervention, the other village gets the control, and they think they have this really great randomized trial with 2,000 people, but really, insofar as the analysis is concerned, the key end there is 2 because you've only got the 2 villages. And you can kind of see why that's a problem, because if there's any intrinsic differences between those villages, that would confound the treatment effect. So you have to replicate the number of villages in the intervention group and replicate the number of villages in the control group. So why do people use this design? The most common reason is that the intervention is intrinsically applied at the community level. So imagine that you were trying to, have some sort of smoking cessation campaign. You were taking out TV ads and billboard ads and radio ads. Well, those aren't directed at individuals. Those are directed at the entire community. And so you can't randomize individuals within that community to either look at the billboard or not, sort of thing. So community level intervention is the most common motivation for this sort of design. Sometimes it just becomes more logistically convenient. Back in the early 2000s, there were a number of HIV prevention studies that looked at adult male circumcision as a prevention tool for HIV. Individuals who wanted to be circumcised as adults were randomized to either immediate circumcision or delayed for 18 months. And so then the incidence of HIV over that initial period, those first 18 months, was compared between the immediate and delayed groups. Clearly, that it can be done as an individual level randomized trial, and 2 of 3 key trials in that area were done as individual randomization, but one was done as a community randomization. Basically the community randomized trial was set up that way because a mobile van would go into a community and offer circumcision over a short time period to all the men in that community, and then go to another community and so forth. So it was more logistically convenient in that case to do it as a community randomized trial. You also may want to avoid contamination. So if you feel like people, it's like if your unit of randomization is a household and you're giving people some drug or device or something to use in the household, you might be concerned that people in the same household would share the intervention. So you might want to randomize the entire household so that everyone in the household has access to it. There's a really interesting aspect to these cluster or community randomized trials when you're dealing with infectious disease interventions, because you can, in principle, sometimes, if it's appropriate, develop an intervention for infected people that is designed to reduce transmission to uninfected people. And so in that case, you're applying the intervention to one group, infected people, but measuring the outcome on susceptible people. And a good example of this is, again, my background is in HIV, giving antiretroviral drugs to HIV positive people to suppress their viral load then reduces their risk or can eliminate the risk of transmission to susceptible people. So you might, well, there has been community randomized trials where the intervention is testing and giving antiretrovirals to positive people and measuring incidence in the HIV negative people. So key statistical implications of this cluster design is that you have to remember then that individuals in the same cluster are going to be what we call correlated or more alike than individuals in different clusters. And that has really important implications for both the design and the analysis of cluster randomized trials. You can't use sort of the real simplistic statistics that we use when we assume data are independent for a clustered randomized trial. Typically, sample sizes are larger in cluster randomized trials. There's this sort of one real simplistic rule of thumb for sort of the simplest sort of cluster randomized trial, where the total number of individuals that you enroll in a cluster randomized trial is equal to the number of individuals you would have in a comparable individually randomized trial times this multiplier or design effect. And there are 2 key features of this multiplier here if you look at it closely. One is the number of individuals per cluster. That's this M. So, I mean, if M is 1, then you have effectively an individual randomized trial. And so this whole thing goes away and these 2 are equal. And the only other way, though, that this thing can be as small as 1 is if the correlation, this row characterizes the correlation between 2 individuals in the same cluster. If that correlation is 0, then effectively you can treat the data as independent and just do a typical analysis. But in all other cases, most commonly, rho is greater than 0 and M is greater than 1. And so this whole term becomes greater than 1, meaning the number of individuals in the cluster randomized trial is bigger than the number of individuals in the corresponding individually randomized trial. So that's sort of, sample sizes are bigger. That's a take-home message here. And then also when you do the analysis, you have to use methods that do account for this correlation. Okay. So what are the common trial designs? Well, basically, they very closely mimic the basic ideas that you have in individually randomized trials. So what we call a simple parallel design cluster randomized trial is essentially, in this little example here, I'm pretending I have 6 clusters and I randomize 3 of them to receive the intervention, 3 of them to receive the control. Remember, in every cluster, there'll be many, many individuals. I'll follow those individuals, enroll and follow those individuals over time, applying the intervention to this cluster, measure the outcome on those individuals, and that will basically be the basis of my analysis.
Dr. Hughes?
Yeah, sure.
Sorry, there's a question in the chat. How do you approximate rho?
Okay, good question. How do you approximate rho? So that's going back to this previous slide. So when you are designing a trial, when you have data in a trial, you can actually estimate rho using some of the common analysis techniques. You can actually get an estimate of rho from your data. And it's very important, actually, when you write up results of trials to report that estimate of rho for people in the future, because that brings us back to how do you design a trial like this. It's very important. You're going to need to have some estimate of rho when you're designing a cluster randomized trial, and where does that come from? And there's no simple answer. In the best case, there is literature in this area where people have looked at this and been able to actually provide estimates of rho in a similar setting that you can use as a basis of your sample size calculations. You might have some preliminary data from various clusters that would allow you to estimate the correlation within clusters. And sometimes it's really just, basically scientific insights or knowledge that's based on. So there's no simple answer to that. There is a reference that I'll provide at the end of the talk where we do discuss some ways of, basically during the design phase coming up with reasonable guesses, if you will, about that. Any other questions before I move on? Okay, so parallel design cluster trial, very similar in principle to individually randomized trial. Big difference, though, is in most individually randomized trials, there are hundreds, even thousands of people enrolled in the trial and randomized. And when, like, HIV prevention trials, 2,000, 3,000, 4,000 people, when you have that many people in the trial, getting any chance imbalances between the intervention and control arms is trivially small, very, very small probability. So we never really even worry about it. But cluster trials, you're talking about having, maybe 20 clusters, 30 clusters. That's not too many. And so it's possible, even with a perfect randomization, to get imbalances just by chance. Maybe more large clinics in the intervention arm, maybe more rural clinics in the control arm. So these chance imbalances can happen just because you don't have lots of randomization units. So that is one concern about this design. And then there are sometimes just logistical issues. Is it possible to implement the intervention in all these clusters at once? And if you're a bit slow on some of the clusters, then you would be concerned about, are there underlying time effects that could be confounding any intervention effects? So you have to be a little careful about things like that. So to deal with that, I would say the most common cluster randomized trial design is a variant on this, which is a match pair parallel cluster design. And it's very similar to the parallel design, except that you first match the clusters according to some key criteria that you think might influence the outcome. So you might want to match rural clusters together and urban clusters together, or large health clinics together and small health clinics together. Anything that you want to make sure is evenly matched between the intervention and control arms, you would try and match your clusters on that. And so then you're kind of guaranteed to have good balance, at least on these factors, between the intervention and control arm. And another advantage of this is because the key comparison, intervention versus control, only happens within a matched pair. In other words, I'm going to compare this cluster to this cluster, but I'm not going to compare this cluster to this control cluster. Okay, so for that reason, if there is logistical issues. Question? Yeah. Okay. If there are logistical issues with starting, all the clusters at the same time, well, you don't have to worry about that so long as you start the pairs at the same time, because again, the comparison is within the pair. So that I'd say is the most commonly used cluster randomized trial design, is some sort of match pair design. In terms of approaches to analysis, if the size of the clusters, and I mean the number of observations in each cluster, are similar, then in fact, there is one fairly simple approach where you can just form a cluster level summary. So simply a mean for that cluster, or a probability proportion for that cluster, or rate for that cluster, and compare those cluster summaries between the two study arms using fairly simple measure, t-test, paired t-test, something equivalent to that. And so if you've got 20 clusters, you might have 5,000 people, but the analysis boils down to these 20 numbers, one for each cluster, and it's fairly straightforward. And that works very well when you have similar numbers for each cluster and you're not trying to do any adjustment for individual level characteristics. It's also possible, though, to use more sophisticated methods and analyze the data at the individual level. These methods then have to be methods that do account for the correlation of individuals within the cluster. Some common methods you may or may not have heard of: generalized estimating equations, mixed effects regression models. These all account for correlation.
Dr. Hughes?
Yeah.
One more question.
Sure.
Does the matched pair design affect how the correlation parameter is estimated?
Yes. If you have matched pairs, it becomes more difficult to estimate that correlation parameter from the data. I won't go into details, but yeah, it would be more difficult to try and get at that. In fact, I guess technically it's impossible from a purely matched pairs design to estimate the correlation parameter, but it's not critical if you were just comparing the pair level summaries or something like that. But you still want to account for, okay, we're getting into some sort of details here. So if you use the matched pair design, it is likely that that will significantly reduce the correlation that you need to account for in the sample size calculation. So I'm just thinking of it going back. There were a number of trials looking at HIV prevention, and values that were used for unmatched designs were much larger than values that were used for matched designs in terms of planning the trial. So there you'll have to get into a little bit more of the literature on that. Okay, so these regression methods on individual level data do account for the correlation, but you have to be a little bit careful, especially with GE. They can be not robust in the sense that not necessarily maintaining its true alpha level, so you can have an inflated type 1 error rate if you have fewer than, say, 10 clusters per arm, and there are some fixes for dealing with that. Okay. Now, I kind of want to make a contrast here between research studies versus implementation studies, because the parallel and match parallel design are very good for research. When you basically have are trying to investigate, have a new intervention, and the question is, does this intervention work at all? You know, we don't have much experience with it, and so, you know, sort of, yeah, just trying to figure out if a new intervention works. But they're less well suited to what we call rollout or implementation study, where this would be a situation where there's maybe an intervention that's been proven to work in a fairly controlled setting, and now the Minister of Health in a country wants to roll it out across the entire country. There's not a question of whether we're going to do it, but just, you know, we want to roll this intervention out. We think it's effective, but maybe we don't know in real life exactly how effective it is. We'd like to get some data on that, try and understand its effectiveness in a real life rather than a research setting. In that case, these parallel and match parallel designs aren't really ideal for that, because half the clusters don't even get the intervention. And if your kind of plan is to roll this out across the country, you would want to make sure all the counties or provinces or whatever get the intervention, eventually all the health clinics. So how do you deal with that sort of situation? And sometimes people try and just look at a simple before-after design. You know, okay, we have data from you know, the country records of what disease rates were before this intervention was rolled out. We look at after and try and do something fairly simple like that. But that can be sort of weak causally, because clearly the introduction of the intervention is completely confounded with any underlying time trends in the disease. So if you see a change when the intervention is introduced, is it truly because of the intervention or other factors? So one way of dealing with that has been this stepped wedge design, sort of a newer idea. The paper that Gary alluded to, we published in 2007. And the use of this stepped wedge design has been growing a lot since then. So the idea of a stepped wedge design is not randomizing the clusters as to whether or not they get the intervention, but rather as to when they get the intervention. So in this example here, all of these clusters start in the standard of care or control condition. And then one cluster is randomly selected to introduce the intervention. Once the intervention is introduced, it's maintained. Then another cluster is randomly selected and to start, and so forth. And so the intervention is rolled out across the clusters over time here. So this is better than a pure before-after, because at each time point we have clusters in the intervention and clusters in the control. And so we have that comparison, that sort of vertical comparison. We also do have before-after comparisons, though we have to be very careful about those to make sure that we're controlling for underlying time trends. And in fact, that is the key weakness of this design, is there is this intrinsic confounding between any underlying time trends and the introduction of the intervention that you then have to try and disentangle in the analysis. So key realization, time is not unlike the parallel and match parallel, time is not balanced between the intervention and control periods. And because of that, you need to be able to take outcome measurements on each cluster at each time period to control for the time trend. So what I'm saying is we have to have outcome measurements on each cluster here and here and here and here and so on, so that we can understand the underlying time trend versus the intervention effect. The stepped wedge designs have been conducted with both cross-sectional sampling, so basically just taking cross-sectional samples at each point in time, or enrolling a cohort of individuals and following that cohort over time. So both sorts have been done. I'd say probably more examples of the cross-sectional sampling than the cohort, but you can find examples of both. So the advantages of this design is that you can easily evaluate the true underlying real-life community effectiveness of a new program during rollout. It can also help with acceptability issues in the community, because you can argue that basically all clusters are now receiving the intervention. You don't have to explain why we're randomizing half the communities to get this intervention, which might be perceived at least to be favorable, and half aren't going to get it. Now, you can also argue the other way. If we know this intervention is effective and we want to give it to everybody, why don't we give it to everybody right away? Why do this rollout? And there it becomes more logistical, practical, financial issues that practically it's not like when you're starting a new health program across the entire country that you can snap your fingers and everything happens, tomorrow. It usually does involve a rollout of the intervention. So if it is going to involve some sort of implementation period, why not take advantage of that to gather some data and do it in a systematic way that can give us some data to really evaluate the effectiveness of the program? And then it's sort of interesting too, because as I mentioned, you not only have the comparisons between communities, but you have comparisons within the same community. Units act as their own control. So likely fewer clusters are needed with this design compared to a parallel design. But disadvantages. First off, you have to roll it out across all these steps. So typically, not inevitably, but typically, these designs take longer to complete. You have to roll things out, be taking all those measurements, and that just takes time, which can increase, possibly, depends on the intervention, depends on the outcome, but the potential for contamination, clusters that are scheduled for a later start may be tempted to try and implement the intervention early, depending on what the intervention is and their ability to do that. And this second comment is really sort of increased potential for external events to influence the study. This is really true, I'd say, of all cluster randomized trials. Almost every trial I've been involved with, there has been some unexpected external event that significantly influenced the study. When I talk about the Washington State Expedited Partner Treatment Trial, I'll give you an example of that. But, political decisions that influence the study, World Health Organization changes in policy that influence the study. You have these external events that seem to be much more commonly influencing cluster trials and individual trials. And so there's sort of just this, the longer the trial takes, the bigger there is a chance that something's going to happen. And so, that's not a theorem or anything, but it's just one of those things that kind of in the back of my mind is the longer a trial goes on, the bigger chance there's going to be a problem. Other interesting aspect of the step wedge design is that even if you have equal loss to follow-up by cluster, that could result in unequal loss by intervention arms. So imagine that you have very good retention early in the trial, but then people start to drop out later in the trial. Well, later in the trial is when almost all of our intervention data is coming from, whereas early in the trial, we're getting most of the data as control data. So you then are creating an imbalance in the loss to follow-up between the intervention arms, even though it's sort of the same for all the clusters. So that's an interesting aspect of this. And then, of course, as I've already mentioned, this intentional confounding of the time and treatment effect have to be resolved by some, more complex analysis than something more complex than just doing a t-test, so some regression analysis or something like that. Okay, not going to spend lots of time on statistical models, but I do want to sort of present this as a way to sort of get you thinking about what are the key assumptions in a stepped wedge design. So hopefully you're all familiar with basic linear regression models. So that's what I've written here is imagine I'm measuring some outcome on individual K in cluster I at time J. And so I want to create a model that will say what will influence the outcome of this individual in cluster I at time J. And so we want to account in our model for any underlying time trends. Remember, it's very important to control for time in a stepped wedge model. So I'm going to have this beta J, which would basically be the effect, underlying temporal effect at time J. Notice that there's no I subscript there. I'm going to assume that that time trend is the same for every cluster. I'm also going to say that, well, not all the clusters are equivalent. And so I'm going to allow the mean of my outcome to vary between clusters. And this is done by introducing what we call a random effect, a random cluster mean effect. And that's this A sub I. And this variation between the means of the clusters basically is what induces that correlation between individuals within a cluster. Individuals within the same cluster are more alike than individuals in different clusters, and that's basically due to this. The part that we're really interested in, though, is the treatment effect. And so that's going to be characterized by this theta, and basically Xij is an indicator that is simply 0 or 1 and says, is the treatment, is the intervention turned on in cluster I at time J? If so, then we should see an effect theta. If not, then we would not see an effect theta. So that's what we call kind of the basic model. This was the one that was introduced by my student Mike Hussey and myself in the 2007 paper. But as I said, lots of assumptions involved. The time effect is the same for all the clusters. The treatment effect has no subscript. So therefore, the treatment effect has to be the same for all clusters. The treatment is either completely off or completely on. It's 0 and 1. There's no time varying. There's no sort of waxing or waning of the intervention effect. And then also cross-sectional sampling here. So since that 2007 paper, there's been a lot of research on stepped wedge, and people have worked on relaxing a lot of these assumptions. And so I'll now just sort of say that maybe I'll call it sort of the standard of practice now would be a more complex model. You'll see now that in this case, there's been some relaxation of the assumptions to allow some variation in the time effect between clusters, some variation in the treatment effect between clusters, still retaining that variation, the mean between clusters. It's getting into a fairly complex model now, as you can see. But one thing that is still sort of a standard practice is to assume that the treatment effect is either on or off, not time varying. And some very recent research in this area has said that has basically shown that even that can be a very dangerous assumption. So I just want to alert you, if you are using this sort of design, to that one issue in just a moment. But I'll just give sort of a foreshadowing of what Emily is going to talk about later in the practical and in the hands-on part of this course. So I'll just remind you that a power calculation or sample size calculations, power is a probability of detecting the treatment effect when the treatment really works. So in other words, assuming this theta is non-zero, we want to be able to reject the null hypothesis that theta is zero, that there's no treatment effect. That will depend on, of course, the strength of treatment. It's much easier to detect really strong treatment effects than small treatment effects, but it's also going to depend on lots of other aspects of the design. The number of clusters, the number of steps, the number of participants per cluster, per steps. These are all part of the design that you would have to put in to figure out the power. The other part is, okay, we talked about this wonderful enhanced model, but it's got all these things that we call variance components. We talked about the variation in the mean between clusters. Okay, what's the variation in the time effect between clusters? What's the expected variation in the treatment effect between clusters? You might think if I knew all this, I wouldn't have to do the darn trial. But those are important and harder to know when you're trying to design a study. And again, we're talking about previous data, previous publications, scientific insights to get some handle on those. And in a reference that I'll give again at the end of the talk, we have some guidelines for how to, sort of make rational decisions about what those should be when you're doing a power calculation. And these are sort of the things that Emily will talk about. Okay, so what we've learned about power so far is power calculations for stepped wedge are hard because of all these things that you have to pre-specify. Also, though, that these new part of the enhanced model, that variations in the time trend or variation in treatment effect tend to have more effect on power than simply that mean difference between clusters. And fortunately, this new publication gathers results from, I think, 40 trials and gives information on what are the values of the time and treatment effects, and for various settings, for various fields of study. So that can be really helpful in terms of, I'm planning a trial, what would be reasonable values to use. This reference as well as the one at the end of this talk. But a warning that ignoring these random time and treatment effects can result in underpowered trial. Okay, how do we do analysis of trials? Well, the one thing you don't want to do, would be tempting to do, but that you don't want to do, is something like a simple paired t-test. So, before when we were talking about cluster trials, we talked about, creating a cluster summary. Well, you could think in a stepped wedge, maybe I could just create a cluster summary for the control period and a cluster summary for the intervention period, and just do a paired t-test on those cluster summaries. But again, that's not valid. It will be likely biased if there's any underlying time trends, because the intervention periods always come after the control periods. So we can't do that. The one thing we can do is, if you go back here to this picture, we could imagine just comparing things vertically like this. So compare this intervention to these controls, these two interventions, these, and so forth. That clearly controls for the time trends. Each of those is within the same time period. So it's like a little mini, parallel design comparison, right? And so you've got all these mini parallel design comparisons that you could do each one of those and then combine the results. That's actually completely valid. The only downside is it loses a lot of efficiency because it throws away the information, sort of the before-after information. So there is good information on the treatment effect from these before-after comparisons if they're done correctly. And so if you completely ignore them, you do lose efficiency. So that's a valid approach, but it's not the most efficient. The most efficient are to use these more complex things based on generalized estimating equations, generalized linear mixed models, which use both the within and between cluster information. They analyze the individual level data. So if your clusters vary in size, that's not a problem. Again, with small numbers of clusters, these can have inflated type 1 error rates. There have been some ways of sort of dealing with that bigger problem, especially a problem with GE. Now, all of these methods, though, are still relying on this idea of an immediate treatment effect, that once you introduce the treatment, you get the full effect immediately. And I want to mention this recent research that has pointed out that that's a much more dangerous assumption than I think anybody in the field had realized. So I want you to consider basically all the models I've been showing, forget all this other stuff, immediate treatment effect model. X is 0 or 1, 0 when the treatment is not in cluster I at time j, 1 when it is, and you get the full effect immediately in that cluster at that time when you introduce the intervention. You could imagine, though, that the intervention could be time varying. So we'll let S indicate the time since the intervention has been introduced. So this would be like before the intervention is introduced to be 0, but then you introduce the intervention and it's 1 at the first time step, 2 at the next time step, 3 at the next time step after the intervention has been introduced. And so then this model would allow the treatment effect to vary depending on how long it's been since the intervention was introduced. That's the key idea here. So we asked the question, what happens if the true process, the true data generating process is this time varying treatment effect, but we kind of naively analyze it using the standard stepped wedge approach, immediate treatment effect approach. And we looked at several different scenarios. These are 4 scenarios that we looked at. The first is, in fact, the instantaneous time effect. So in this case, the immediate treatment effect is a correct model. In this case, there's a bit of a lag. So we have basically no effect. And then we get, bang, suddenly everything clicks on, so forth. Here, things are growing over time. The x-axis here is the time since the treatment has been introduced. And then I just scale it from no effect to full effect here. And then this is just one other sort of thing. So we can say, okay, suppose this is what really happened, but we analyze it assuming an immediate treatment effect. What would you expect should happen in terms of our estimated treatment effect? Well, in the first one, you would certainly hope that it would, estimate the full treatment effect. That makes sense. But it's more interesting to ask, what do you think it would do in these cases? And, sort of the logical thing is, it ought to estimate something, some sort of weighted average here. Well, let's just say, okay, I got, like 4 time points when it's completely effective, 2 time points when there's no effect. So maybe the average would be around 2/3 or something like that. That's what I expect. Some sort of average here, some sort of average here. That's what we would expect and hope that the treatment effect estimator would be doing. But unfortunately, that isn't what it does when you naively apply the immediate treatment model. In fact, this is what happens. When the immediate treatment model is correct, then you correctly estimate the full immediate treatment effect. No problems there. But when that immediate treatment effect model is wrong, things go really wonky. This is the true curve that generated the data. Our estimated treatment effect is actually of opposite sign to the observed treatment effect. Here, it is doing something reasonable, but here, again, we get something really wonky happening that, here's the true effect and here's our estimated effect, essentially zero. What is going on here? And so we've basically put out a paper. We submitted a paper to Statistics in Medicine, but you can download the paper here. What is basically happening here is that the estimated treatment effect from the immediate treatment model ends up being a weighted average of all of these individual effects. But importantly, some of those weights can be negative and others can be greater than 1. And so what happens in this example is these time points get a weight of greater than 1, but these time points get negative weights. And so hence, this is the estimated treatment effect. So it's really bizarre. So it really points out a real limitation or concern about stepped wedge trials is if you anticipate that the treatment effect will be anything other than the immediate treatment effect, you should not use a standard approach for analyzing stepped wedge trials that assumes an immediate treatment effect. You should use one of the new approaches that we've described in this paper. And it can be very dangerous if you do naively assume an immediate treatment effect when that's not true. How are we doing for time here? Okay. Okay, so what I want to do now is talk about my experience with one stepped wedge trial I was involved with. It's the Washington State Expedited Partner Treatment Trial. Expedited partner treatment was essentially a way of dealing with cases, basically is meant to reduce incidence of gonorrhea and chlamydia, bacterial sexually transmitted infections in Washington State. Expedited partner treatment has 2 pieces. One is patient-delivered partner therapy. So standard of care prior to this would be if a person comes into a clinic or a doctor and tests positive for gonorrhea or chlamydia, they would be treated, and then they would be asked to refer their partners in for treatment. As you can imagine, that message doesn't always get through. So an alternative is to actually give the index patient drugs, or in this case, vouchers for drugs to give to their partners. So patient-delivered partner therapy involved giving the original index patients a voucher that they could give to their partner that could be taken to essentially any Walgreens or Walmart drugstore. I think there are others involved in Washington State, and redeemed for free drugs for treatment for the appropriate disease. Partner services then is there to assist the index patient if the index patient is unwilling or unable to basically contact their partners, then individuals from the health department will contact the partners and deliver the drugs or the vouchers for drugs. So the kind of these 2 pieces of this program. This program had been shown to reduce reinfection in the index patient in individually randomized trials. So it was thought that it would be effective and could be effective in reducing rates of gonorrhea and chlamydia disease in the state as a whole. So it was going to be implemented throughout the state, but it wasn't something that you could immediately do. Matt Golden is a professor in medicine, was the lead on this, and him and his team were going to have to go around to the counties, helping them implement this program. And so what we settled upon was to use a stepped wedge design. Originally, we thought we would have 24 what we call local health jurisdictions, usually corresponded to one of the counties in Washington State. In some cases, it would be 2 or more counties together. And we were going to randomize 6 of these local health jurisdictions per time. This is sort of the picture. We called them wave 1, wave 2, wave 3, wave 4. And then we had sentinel sites across the state that reported gonorrhea and chlamydia. Well, gonorrhea is a reportable disease to the state, so we could get state data on rates of gonorrheal disease in the state. And chlamydia, we were measuring at these sentinel sites throughout the state. Now, the whole issue of how long is it going to take to implement this, what we did was we planned for about 6 months intervals between steps. And the idea was that we would take 3 months to implement, and then hopefully the intervention would be having an effect in those counties after about 3 months of implementation. And so then the latter 3 months is when we would actually collect data to use in the assessment of the intervention. So that was sort of the plan. And this is basically how it was rolled out. In the end, we only ended up having 5 instead of the originally planned 6 in wave low-cost jurisdictions in wave 4. Okay, so one thing we asked is, we did some studies to find out what proportion of partners actually were getting this patient-delivered partner therapy. Informally, some providers had been doing this even before we introduced the intervention. And so you can see that prior to the intervention, some percentage of partners reported having received partner therapy like this. What we would hope is that it would improve after the intervention. In fact, ideally, we'd hope it would go up to 100% after the intervention, but it didn't. So this is sort of incomplete delivery of the intervention, as you can see here. It certainly went up, but certainly not as much as we might have hoped over time. The other piece of the program was the partner services. So health clinic personnel helping deliver the intervention if the index patient wasn't able to. And what we see in the first 2 waves here is a decent increase in provision of these partner services before and after. But wait a minute, what's going on here in waves 3 and 4? Well, doesn't seem to be much difference before and after in provision of partner services. You remember how at the beginning of the talk, I was saying that in cluster trials and step wedge trials, these external events can influence your trial? Well, it so happened that right in the middle of this trial, the state of Washington legislature had some extra money and decided to give it to health departments throughout the state to provide partner services to individuals diagnosed with sexually transmitted infections. So basically, the state instantaneously funded this entire portion of the program. And so we see that suddenly these numbers increase in the pre-intervention period because of that influx of state money. Things go wrong in cluster trials. Okay, what about the actual outcome? So what I've got is each of the 4 waves. So the open circle means pre-intervention, the closed, or not circles, open squares and closed squares. The closed squares are post-intervention. So let's look at wave 1 here. That was the first 6 communities to introduce the intervention. And we see this is the rate of positivity in women 15 to 25 years old in these sentinel populations. And gratifyingly, it goes down as we introduce the intervention, a little blip here at the end, but generally a downward trend. How about the second wave? Well, we see, pre-intervention, post-intervention, there's a downward trend, so that's encouraging. We look at the third wave, well, wait a minute. Things are kind of going downward even before we introduce the intervention, and then we introduce the intervention, it continues to go down. And same thing here, things are going down, 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 even before we introduce the intervention. Well, this is why it's very important to control for time trends in a stepped wedge trial. In fact, in subsequent research, Matt and colleagues found that there was decreases in STIs over the course of this study, not only in Washington state, but in Oregon, Idaho, other Northwest states. It's not completely clear why, but this was an overall temporal trend in the area over time. So the question then is how much of it is actually due to the intervention? We have to disentangle the time trend from the intervention effect. This is the results for gonorrhea. We see a very similar picture, decreasing trends, both even before you introduce the intervention. So we did an analysis of these data, and basically what we found was modest reductions associated with the intervention, risk ratio of 0.89, so 11% reduction in chlamydia, 14% in gonorrhea, neither really statistically significant. Okay, so what are some issues then that we were kind of thinking about after this trial? Well, one is the one I've already mentioned, the fact that part of our intervention was provided basically by the state outside of the investigator control. Other issues that you need to think about, potential for contamination of the outcome. Clearly, sexual partnerships don't respect boundaries of counties and so forth. So you would expect that an intervention that's effective in one county could have at least effects on neighboring areas of adjacent counties. What about the intervention? What about when doctors talk to each other or go to meetings and say, we're doing this in our county, and it's certainly medically permissible to give patient-delivered partner therapy. It just wasn't standard of practice. So it's something that a doctor could adopt even without this intervention. What about this issue of lagged effects, right? So I made a big deal of that when we were talking about the assumption of an instantaneous treatment effect. That's something that I never looked at when we originally did this study. So it wasn't on the radar that this was an important issue, but it's certainly something I've looked at in light of those results I was showing you. So I basically used an extended data set. Remember that with the primary analysis, I only used the last 3 months of every 6-month intervention period. I used now all the data to try and look at this whole issue of a lagged effect more closely. Now for chlamydia, instead of about a 11% reduction, there was about a 5% reduction in rates. But this was what, oh my God, you know, so this is what I found. What these indicate is the log relative risk for each time on treatment. Okay, so one 3-month period on treatment, two 3-month periods, 3 3-month periods, and so forth. So this is time on treatment. Notice that all of these are all actually greater than 0, meaning a relative risk greater than 1. This is the estimated effect from the fitted immediate treatment model. So we see exactly that problem I alluded to earlier. The immediate treatment model effect is in the opposite direction of all of the individual time on treatment effects. Okay, now I then did apply our methods that basically average these, and basically we get, instead of a non-significant small decrease in risk, we get a non-significant small increase in risk when these are appropriately average. So I guess the message is the same, no significant treatment effect, but it is quite interesting that we see this phenomenon that I alluded to earlier in real life, and it really reinforces that you have to really be thinking about in a step wedge design analysis that immediate treatment effect.
How,
Yeah, go ahead, Mary.
how does that relate to your former slide where you had kind of no treatment effect, but a
Yeah.
yeah,
So you're saying this one,
the
yeah.
bar plot.
Yeah. So in this one, we actually see, positive effects here and negative effect here. So reversal. These are not outcomes. This is basically process. This is treatment provision. So we do see in treatment provision increasing. In these, basically, okay, how much of this is time trend? How much of this is treatment effect? It does look like this, is that there's still some modest treatment effect. So that seems a little bit different than what we're seeing here. Yeah. So I think the one thing that to remember here is there's huge variability, especially around these points. So basically, I think there's nothing significant here, but yeah, I can see what you're getting at.
There's a question in the chat as well.
Yeah, what's that?
Are delayed treatment effects still an issue for matched parallel cluster study designs, or not so much?
Not so much, because you don't have the confounding time on treatment, confounding of time and treatment in those. So there, if you have a delayed treatment effect, it would kind of act the way you would expect it, which is that it would reduce the overall treatment effect, but it would not have these wonky reversals and so forth. And just to make one other comment about that, like if I knew, going back, this one, if I knew or suspected that this was going to be the case, that I was going to act like this, then I could, and I actually allude to this, I think, in one of my coming up slides, I could a priori decide to not use these data in the analysis and only use these to estimate the treatment effect. And then if I made that assumption and threw away this data and only used these, then the model would work fine. I'd be assuming an immediate treatment after 2 time units, and I get the exactly appropriate analysis. So if you have some insights like that, or are worried about this, you want to decide to throw away like the first 2 periods after implementation, then that can also solve this problem. It's only when you basically use all the data in the analysis that you get this problem. Okay, so is step wedge the right design? It's useful for implementation studies. But I think if I was evaluating a new intervention, I would really prefer to do a parallel or matched parallel randomized trial. Basically, step wedge is not as good a design as a classic parallel or matched parallel design. It's more of a design of last resort in some sense. You have this confounding of time trends with intervention effects, so you always need to control for time trends. And this issue that I've brought up about lags in the intervention effect can cause bias as well as reduced power. step wedge can be difficult to implement when the individual receives the intervention repeatedly over time. And one example that I've run into this a lot is prevention of mother-to-child transmission of HIV. So a mother will be enrolled during pregnancy and receive some intervention during pregnancy, and the outcome is the infant being born HIV uninfected. And so then in that case, what happens when a clinic transitions from the control to the intervention in the middle of a woman's pregnancy? Then she'll have received during part of the pregnancy, she would have been in the control condition, and during part of the pregnancy, she would have been in the intervention condition. And how do you deal with things like that? And so then you can add a transition period. And this would also be what you would use in that example I was just talking about. If you expected the intervention wouldn't be effective for, say, the first period, you decide to throw out the data from that period. So I'm going to use the data from this period. Women that are enroll and deliver in this period, or that enroll here and deliver here, I'm not going to use them. And I'm only going to use births from women that receive the intervention during their entire pregnancy. So I'm going to use this transition period to throw out those awkward cases where women receive both control and the intervention, or throw out these periods when I think the intervention might not be effective, and then try and use these data to estimate sort of the longer term effect of the intervention. If the step wedge is going to be used, then you want to think carefully about what is it that you're estimating. So if you really truly believe there'll be an immediate treatment effect, then fine, you're estimating, then it's very clear what you're estimating. It's just the size of that step. But what if, what if you are in a situation where, you think that something like this is going to happen? What exactly is it that you're trying to estimate? Do you want to estimate the mean over this period? Do you want to estimate the long-term effect? Do you want to estimate the effect at a particular number of time units after the intervention has been introduced? There, it's going to take a little more careful thinking about what is it you actually want to estimate, and designing the study to estimate indeed that quantity.
While you're on this slide,
yeah.
There's a question about this slide. Do you have any insight as to why the instantaneous treatment model performs somewhat to expectations in the curved scenario, but so poorly in the partially convex model?
Yes, I think it again comes down to the weighting issue here, that these points, especially this last one, is getting a large negative weight. These points are getting, or at least a negative weight, I shouldn't say large negative, but a negative weight. These are getting large positive weights, even greater than 1, but they have very little treatment effect. So you're like, a bit, this contributes a lot, but it's a small effect. So it is, you're not getting an equal average of all these points, which is arguably maybe what you should want to do in this case. You should probably want to, estimate what is the average treatment effect, or maybe you want to estimate, this longer term effect. But because of this weird weighting that's going on, the instantaneous treatment model does not do that. So yeah, consider the estimate, measure the outcomes at the same calendar times in all clusters. You have to basically synchronize your outcome measurements across all the clusters so you control for time trends, and try and maintain engagement with the control clusters to avoid them dropping out. I've already mentioned the possibility of changes in policy or other external factors that are not under the investigator control. I think that's it. So yeah, so this was the one paper I was referring to. In this paper, we talk a bit about approaches when you're designing a trial to estimating those difficult to know variance components. And so some rules of thumb you can use in addition to the paper by Kosovar and colleagues. And then this is the one on that I've shown the figures from, where demonstrates the danger of that immediate treatment assumption. That's all I got. Basically, I can take some questions at this point. Let's see. Oh, yeah. It's I think basically some questions, and then we'll take a break.
Jim, thanks for this excellent workshop. Really appreciate it. It's Julia Hood at Public Health Seattle King County. I'm a little bit curious about how the data units, whether they're measured at the individual population or subset of the population. If you could speak to it a little bit more.
So usually measurements are taken at the individual level. So for instance, in the Washington State Expedited Partner Treatment Trial, we had the state reporting data on individual cases of gonorrhea, which we could then map to the appropriate county. And we had individual results on chlamydial cases from the sentinel sites in the study. If the number of individual observations, outcome observations, is the same in every cluster at each time point, which would typically be by design. I'm planning on taking 30 blood samples from an individual, in each cluster at each time point. Then you can aggregate to that sort of cluster time period. Just take the mean of your 30 or the proportion of your 30 observations and do the analysis on those cluster period averages. But more commonly, certainly in that case, we had different numbers of observations for each cluster and for each period. And in fact, I think, Emily, are you going to use those data for some of the hands-on workshop?
Not the varying number of individuals.
Oh, okay. But we did have varying numbers of individuals in each cluster in each time period. So when we did the analysis, on the individual level to account for that variable numbers. Is that getting at your question, Julia?
Yeah, thank you. And the stepwise interventions that have been done in global health settings, is it possible, or are they been implemented more on population level data rather than individual? Where surveillance systems like registries.
Right. So sure. So you could do it on the population level data, but you would lose some efficiency, if you don't account for the fact that basically the denominators are different. So it should still be valid, but you would lose some efficiency.
Thank you.